If you look at page 9, there are 4 polynomials that you need to look at. Each one has 3 factors to test. I do want to give you credit for this assignment, so when you're done, hand it in. It's not due till tomorrow. We'll just do a part of it today. And we're going to find out if these are factors using synthetic division. So, my coefficients for the first one are -2, 15, and -7. If I want to test x plus 1, what root do I use? I use -1. So I'm going to bring down the -2. -1 times -2 is 2. 15 and 2 is 17. -1 and 17 is -17, which gives me a remainder of -24. Is x plus 1 a factor? No. How do I tell? The remainder is not 0. In order for a binomial to be a factor, the remainder in synthetic division has to be a 0. Isn't -1 times 17 is -17? Okay. So let me back up and try a different factor. So let's try 7. So I bring down the -2. 7 times -2 is -14, which gives me a 1, which gives me a 7, which gives me a 0. So is x minus 7 a factor? Yes. Now, I don't even need to do any work. I can tell that x minus 2 is not a factor. What is it about my result that tells me that the next factor is not actually a factor? What do these tell me? If I divide by x minus 7, this is what's left. Turn this into an equation for me. Well, what did I start with? What was my leading or my biggest exponent in my original equation? X squared. So if I started with an x squared up here, what is this one going to be? An x. So -2x plus 1. Well, is this the same as that? No. Now, if you don't understand that, that's okay. Just scrap it and try C and see if it works. Okay, and that little trick won't work on the x to the thirds, because you'll start with an x to the third and you'll end up with an x squared. So you'll just need to test them all. Okay, so that's part of your homework today. Yep. And look at this polynomial functions and behavior worksheet. Hey, you're here. So you need to do page 9 for your homework. So if we look at the middle of the first page, we're going to talk about end behavior, meaning as the graph moves to the right, does it approach positive infinity or negative infinity? Does it go up or does it go down? So if we were to graph x to the third in our calculator, it would look something like this. And you'll notice, yes, draw that please. You'll notice as we move to the right, so as we go to the right, the graph goes up. So as my x's move to the right, my y values move up. And we write that in this form, and it's a little bit strange. We say the limit of x to the third, so the limit of our equation, And then we say as x approaches infinity. Now this is kind of a calculus notation, but it's something that we start using now, and then as you progress on, we do more complicated limits. So all this is saying is, the limit of this particular graph, as my x values get bigger, equals, well, where are my y values heading? Up toward infinity. So, the limit of x to the third as x gets bigger is infinity, which means as x goes towards infinity, y goes towards infinity. Okay? And then we look at the other side. The limit of x to the third as x approaches negative infinity. So as I move to the left, what way does the graph go? Down. Equals negative infinity. Okay? Now it's not on your paper, but I want you to draw another graph. And it's going to be y equals x squared. We know that x squared looks like this. Just draw it off to the side somewhere. So, on an x squared graph, as the limit as x of x squared as x approaches infinity is, so in this graph, as I move to the right, where do my y values go toward? Infinity. And the limit of x squared as x approaches negative infinity would be, so as I move to the left, what direction do my y's go? Up toward infinity. Okay? So the x to the third has one up and one down, and the x squared has two ups. Now, don't draw this one. Do you remember last year when we did y equals, let's say, 10 times 0.5 to the x? What did that graph look like? It started at, say, $10, and it was dropping. And did it ever actually reach 0? No, but it's getting closer to 0, right? Well, we can do something called a limit, and we can actually capture that 0. If we tried to lengthen our graph out long enough, how far would I have to go before I actually hit the 0? I'd never get there. Okay? But mathematically, there is a way to capture that 0. We say the limit as x approaches infinity of 10 times 0.5 to the x is, if I were actually to reach infinity, which can't happen, what would be my answer? So if I were to plug in this number, I would get that. If I were to plug in 2, I'd get that. If I were to plug in 3, I'd get that. If I were to plug in 1,000,000, I would get something like 0.00000007. I don't know, something like that. That's my guess. Okay? Which is really close to 0, but it's not 0. But if I actually reach infinity, then the answer is 0. And that's a huge part of calculus. In algebra, we can never get there. We can get so close, but we can never reach it. But in calculus, we're allowed to use infinity. And with infinity, we do hit the 0. Now, basically, that means we can get so close that we don't care. Let's say you were building a house, and it had to be perfect. The dimensions of the house had to be perfect. How hard would it be to get all of the measurements exactly perfect? You can't. It's impossible. But if you had enough time, could you get really close? Well, if I said everything accurate within an inch, would that be hard to do? No. If I said a half an inch, would that be hard to do? Probably not. What if I said 1/100th of an inch? Is it possible to get within 1/100th of an inch? Yes, but it would take more time. Okay? What about 1,000th of an inch? It would take a lot more time, but I could get there. So basically what this says is, if you tell me how close you want me to get, eventually I can get there. It might take me a long time, but I can get as close as you would like. I can't ever actually hit that 0, but with this notation you see, it's heading towards 0. Okay, pick up your pencils again. So on some of the other pages, you have 3 functions that you need to graph. So graph those 3 functions, and then turn the page. On the next page, you have 6 functions to graph. 3 there, 3 there. And then on the last page, you also have 3. Well, the very last page you can scribble out. So just totally cross off or tear, or I don't know if you can tear it off. No. So scribble out just the very last one. Not the last 2. Not that one, the other one. No, the last page. Is it totally separate? Okay. The very last page. Okay, yeah, just tear it off and throw it away. But I want you to go through and graph all of those functions. So I think you have 4 different sets of 3 that you need to graph. So graph them on your calculator and then draw a graph. You do need to change your window. Change your y's to go from -25 to +25. Keep your x's the same, but change your y's from -25 to +25. So look up here for a second. So you have 3 different sets of polynomials, and within each set, the end behaviors are always going to be the same. So in your first set, your graphs will look something like this. These aren't perfect, so don't worry about them. But they all have the same end behavior, right? Well, your end behavior is the limit, and instead of writing out the whole equation, I'll let you call this one f of x, and this one g of x, and this one h of x. So the limit of f of x as x approaches infinity is what? So this goes below those 3 graphs on that paper. What is the limit as x gets bigger? Infinity. Okay. And what is the limit of f of x as x approaches negative infinity? Negative infinity. As we move to the left, the graph goes down. And that's true for all 3 of them. Now, these are 3 different polynomials. In fact, the degree of each polynomial is different. What do these polynomials have in common? There's a reason why they all have the same end behavior. So the first one is an x to the 3rd. The second one is an x to the 5th. And the last one is an x to the 7th. What do those have in common? They're all odd. And more than that, they're all odd with a positive leading coefficient. Because on the next page, what happens when you change the original number to a negative? Then it flips, and the end behavior is exactly opposite. Okay? What did you notice about the even numbered ones? So if, I don't know what yours looked like, something like this, and then something like that. So these are the x squareds, the x to the fourth, the x to the sixth, and so on. Notice that the end behavior in both directions is up. The limit as x approaches infinity is infinity, and the limit as x approaches infinity, negative infinity, is also infinity. One answer is good enough, because they're all the same, right? Okay? What happens when I change these even-numbered ones to negatives? Then it flips them so they're both down. So, if I showed you this graph, what can you tell me about that polynomial? It's got to be negative x, and it has to be an odd number. Even numbers are either up and up or down and down. Odd numbers are either up, down, or down, up. So this has to be either a 3, a 5, a 7, a 9, or so on. Okay. Could it be a 1? 1 is odd. What do x to the first look like? They're just straight lines. I mean, they can be in any direction, but they are straight lines. Okay? Well, what about this one? Positive, even. Could this be an x squared? No. If you look at the possible roots, this one could have 4 roots. So it can't be an x squared. The number of wobbles kind of eliminate certain x's. The number of direction changes. So watch this. X to the first, x to the second, x to the third, x to the fourth, x to the fifth. If I continued, that would be x to the fifth. But if I turn around again, then it's x to the sixth. Okay? Now, this one could have 1, 2, 3, 4, 5, 6 roots. But does that mean it's an x to the sixth? No, it could also be x to anything higher than 6 that's also even. So it could be an 8 or a 10 or a 12. Could it be a 4? No, it can't be a 4. Okay, so looking at the graph will tell you the minimum number and whether it's even or odd. It will even tell you if it's negative. This one is negative x to the sixth or something bigger than 6 that's still even, because there are 6 wobbles in there. Okay, now having said that, that could be an x to the 20th. But it's at least an x squared, because it has, it starts in one direction and it turns around and goes in another direction. So it could have 2 roots. Okay? So you should be able to finish the rest of that worksheet in class. Look at the very end, look at that chart. If the degree is odd and the leading coefficient is negative, what do we know about the graph? So if it's x to an odd power and it's negative, I know it's going to go in this direction and in that direction. I don't have any idea what happens in the middle. Just draw the picture. Okay? If it's positive and odd, what would that picture look like? The left side goes down and the right side goes up. And then you'll need to do the same thing for the even numbered ones. Okay, you shouldn't have any homework today except for that page 9. You need to finish page 9 and turn that in tomorrow.